So we are on to 2006 MIT Integration B regular season, rounds 2 and 3. And round 2 was a short round where we had only one problem. The definite integral from x equals to 0 to x equals to a half of the x times arcsine of x over 1 square root of 1 minus x squared. Round 3 was quite lengthy, had 5 problems. Problem number 1, the integral from x equals to 1 over pi to x equals to a half of the natural logarithm of the floor function of 1 over x. Problem 2, which was the indefinite integral of 2x times sec x plus x squared plus sec x tan x. Problem 3, the indefinite integral of 2x cubed minus 1 over x plus x to the power 4. Problem 4, which is the definite integral from x equals 0 to x tending to infinity of 1 over x plus the square root of 1 plus x squared to the power 2. And problem 5, which was just a simple problem, which is the indefinite integral of the square of the natural logarithm of x. So we're going to look at all these problems one by one and systematically suggest our versions of the solutions we have. This is the first problem, as we highlighted previously. The definite integral from x equals to 0 to x equals to a half of x times the arcsine of x over the square root of 1 minus x squared. So let's see how we may be able to solve it. How I may be able to attack this problem is, first I would substitute off the most complicated part, and I look at arcsine of x as that component that needs to be substituted for 4. So I say let u be equal to the arcsine of x, such that sine of u is equal to x. And so what that means is that when now we differentiate both sides, we have cosine u du dx being equal to 1. And if we multiply dx to both sides, we get cosine u du being equal to dx. And that means that now we can substitute off this dx component with cosine u du. And now looking at the limits, when x equals to 0, the arcsine of x, so the arcsine of 0 is 0. When x equals to a half, the arcsine of half is pi over 6. Therefore, the integral from x equals to 0 to x equals to a half of x times arcsine of x over the square root of 1 minus x squared is the same as, in the u domain, the integral from u equals to 0 to u equals to pi over 6 of, in place of x, I have sine u, in place of arcsine of x, here I have u over the square root of 1 minus, in place of x squared, I have sine squared u. And then in place of dx, we have cosine u du. Now, focusing on the denominator here, the square root of 1 minus sine squared u is square root of cosine squared u, and that becomes cosine u. So we have cosine u in the denominator, and we also have cosine u in the numerator. So those cosine u's cancel out, and what that means is that these components go out, and we have the integral of now u times sine u. So when we look at this problem, the integral from u equals to 0 to u equals to pi over 6 of u times sine u, I am inclined to use integration by parts. And what integration by parts really means is that if you have two functions, capital V and the derivative of du multiplied together, when you try to integrate that product, you get uv minus the integral of u times the derivative of derivative of v. And so we can now recreate sine u to be the derivative of negative cosine u. And so here we can now relate this relationship in such a way that the capital V can be equated to the small u, the capital U can be equated to negative cosine u, such that now the product uv is negative u cosine u, limits applied appropriately. And since we have a negative here and we have a minus here as well, it means that minus minus becomes a positive, and so we have plus the integral from u equals to 0 to u equals to pi over 6 of cosine u. The integral of cosine u on that second part becomes sine u, and that means that now we can now apply the limits appropriately when u tends to pi over 6. That becomes negative pi over 6 over cosine pi over 6 minus, when u tends to 0, 0 times cosine 0. So this part here definitely tends to 0. And also on the sine part, as u tends to pi over 6, sine u becomes sine pi over 6, and when u tends to 0, it becomes sine 0. So this part also tends to 0. Okay, and so we are left with negative, here we have negative pi over 6 times cosine pi over 6. Cosine pi over 6 is root 3 over 2. And so as we proceed, the cosine pi over 6 will become root 3 over 2, and sine pi over 6 becomes a half. So sine pi over 6 will be positive half, and negative pi over 6 times root 3 over 2 here, and this 1 over 2 will interact so that we have 1 over 2 minus root 3 over 12 times pi. And making 12 the common denominator, we have 6 minus root 3 pi. So we'll continue. One expression becomes the integral from x equals 0 to x equals to a half of x times the arcsine of x over square root of 1 minus x squared equals to 6 minus root 3 pi over 12, and that is the final answer. Jump on to the round 3. Round 2 was very short. There was only a single problem for which they were able to get the winner. But round 3 had a couple of problems, actually 5 problems to be exact, as I mentioned previously. This is our problem number 1. The definite integral from x equals to pi over 1 over pi to x equals to a half of natural logarithm of the floor function of 1 over x. So looking at this problem, how may we be able to tackle it? The first thing is, let's try to understand what a floor function is. So the floor function of a function fx is equals to k when fx is greater or equal than k and less than k plus 1. So in the interval between k and k plus 1, fx, the floor function of fx is k. Now, what about for 1 over x? So 1 over x is equals to k when 1 over x is greater than k, greater than or equal than k, and less than k plus 1. What that means that when we now get the reciprocal, we see that when 1 over k is greater than or equal to x, and when x is greater than 1 over k plus 1, in that interval, the floor function of 1 over x is equals to k. So coming down, it means that when x is between a half and a third, the log of the floor function of 1 over x is equals to log of 2, because the k in that instance is 2. And in between 1/3 and 1 over pi, the natural logarithm of floor function of 1 over x is natural logarithm of 3. So what that means is that if we have a plot x on the horizontal and y in the vertical, and we have a plot of natural logarithm of 1 over x, it means that when between 1 over pi and 1 over 3, we have just a constant value, natural log of 3. And between a third and a half, we have a constant value of log 2. And so the integral here entails for us to find the area under these constant values. So what you can see is we have two rectangles, one of which is 1 over 3 minus 1 over pi, and then the other one of with a half minus 1 over 3. And obviously the height is log 3 and log 2 respectively. So in other words, our integral now is going to be equal to the integral from x equals to 1 over pi to 1/2 of natural logarithm of 1 over x floor function is the same as the width, which is a third, minus 1 over pi times log 3 for this very first rectangle, and then 1 over 2 minus 1 over 3 times log 2 for the second wider rectangles. And so this becomes pi minus 3 over 3 pi times log 3 plus 1 over 6 times log 2. And this, ladies and gentlemen, was the answer that was required. So problem 2 of round 3 was actually very simple, which is the indefinite integral of 2x secant x plus x squared secant x tangent x. So let's see how we're able to solve this. The problem is easy. Just by quick investigation, I'm seeing that we do have the derivative of x squared as in the form of 2x. So I'm just going to put that as the derivative of x squared times secant x plus x squared times the derivative of secant x. So what we see here is we see the product rule. When you differentiate a product of two functions, v and u and v, you get u times the derivative of v plus v times the derivative of u, and that's what we see. So what this integral becomes, it becomes the integral of the derivative of x squared times secant x. So that quickly just tells us that since the integral is the antiderivative of a function and we have a derivative in there, so the integral negates the derivative, and so the function remains immutable. So we have x squared times secant x plus obviously an integration constant c, and that was the answer that was required. To problem 3, this is a fairly challenging problem. The indefinite integral of 2x squared minus 1 over x plus x to the power 4. So let's quickly see how we may be able to solve this problem. The first thing I see here is I could try to and I apologize here because we do have x to the power 4 here. So what we do is when we pull x squared out, you're left with 1 over x plus x squared in the denominator within the brackets. And as we can see here, if we merge whatever the x squared with the whatever's in the numerator, so we have 2x cubed over x squared minus 1 over x squared, we come to see that we have 2x minus 1 over x squared over 1 over x plus x squared, and 2x is the derivative of x squared and 1 over x squared is the derivative of 1x. So essentially what we have in the numerator is the derivative of the denominator, and we all know that if you have an integral of a fraction for which the numerator is the derivative of the polynomial or the function in the denominator, then the integral of that is the natural logarithm of that function in the denominator plus c. And so for our situation here, so since the denominator is 1 over x plus x squared, therefore the answer is the natural logarithm of 1 over x plus x squared, obviously plus the integration constant. So problem 4 is actually quite challenging. The definite integral from x equals to 0 to x tending to infinity of 1 over x plus the square root of 1 plus x squared. all that squared. We're going to use Euler substitution here, and that is actually, it might be rare, kind of unhard, but it is something. If you see x plus the square root of something somewhere, you may want to try to use Euler substitution. What does Euler substitution entail? Euler substitution entail us saying, let u be equal to x plus the square root of 1 plus x squared, so that when now you say you take x, this x onto the left hand side, u minus x becomes the square root of 1 plus x squared. And so when you square both sides, you have u minus x squared is equals to 1 plus x squared. That means u squared minus 2ux plus x squared is equals to 1 plus x squared. And as you can see, the x squared cancel out. So what you're left with is u squared minus 2ux is equals to 1. Taking the 2u onto the right hand side, what we find is that we have u squared minus 1 over 2u is equals to x. So we just took the 2ux onto the right hand side and we brought 1 onto the left hand side and then divided both sides by 2u. And so x becomes u over 2 minus 1 over 2u. This same expression, just taking each part separately. And then so what we find is that dx du is equals to a half minus actually 1 plus a half plus 1 over 2u squared. And so dx multiplying du both sides becomes u squared plus 1 over 2u squared du. And we could also look at the limits when x equals to 0. Since u is equals to x plus square root of 1 plus x squared, u becomes 1. And so in the u domain, when you're integrating, it's the same as the integral from u equals to 1 to u still tending to infinity of since x plus 1 plus square root of 1 plus x squared is u, we have 1 over u squared times dx, which is u squared plus 1 over 2u squared du from this part. Okay, and so this can be simplified into the integral from u equals to 1 to extend u tending to infinity of u squared plus 1 over 2 u to the power 4. Now we can separate these two components separately so that we're integrating them independently. We have 1 over 2, the integral from u equals to 1 to u tending to infinity of 1 over u to the squared to the 2 plus 1 over u to the 4. And that integrated becomes a half. The integral of 1 over u squared is 1 over negative 1 over u. The integral of 1 over u to the 4 is 1 over 3 u squared cubed. So as u tends to infinity, on the upper side, we see negative 1 over u minus 1 over 3 u cubed. This entire part goes to 0 because the denominator collapses increases too rapidly, and so we are left with the lower limit, because 0 minus, as u tends to 1, we have 1 over u tends to 1, 1 over 3 u cubed tends to a third. So we have 0 minus 1 minus a third, and that becomes a half times 1 plus a third, because this minus interacts with the negatives in the brackets. We have 1 plus a third, so we have a half times 4 over 3, which becomes 2 over 3. And so what we see here is our original problem, the integral from x equals to 0 to x tending to infinity, 1 over the square of x plus the square root of 1 plus x squared, is just as simple as 2 over 3. And that is the answer that was expected. This is the last problem, and this actually was wonderfully solved out by one of the contestants in the record time, which is the indefinite integral of the square of natural logarithm of x. So let's see how we may be able to solve this. One way would be to just look at this and say, okay, let's use integration by parts, right? And considering that there is a hidden one there, we consider that hidden one as a derivative of x. You could choose to go it this way, or you could just choose to say let u be equals to the natural logarithm of x. I choose to just use log x the way it is. And so integration by parts says when you integrate a product of v and the derivative of u, and this is capital U here, you get the product of uv minus the product of u and the derivative of v. And so what that now means is that looking at this expression, our u is x and our v is the square of log x. And so we have x times log x squared for u and v product minus the product x times the derivative of log x squared. So we have log x squared differentiated is 2 times log x times the derivative of x, which is 1 over x. And 1 over x and the x here cancel out. So we have x times the log x squared minus 2 times the integral of log x. Now again, this log x can be seen as log x times the derivative of x, since there is a hidden one somewhere here, right? And so what we can do is we can now say, okay, using integration by parts again, we have 2 times the integral of log x times the derivative of x, and then it becomes x times the square of log x minus 2 times x times the log of x minus x times the derivative of log x, which is 1 over x, and 1 over x times x that cancels, so we get just the integral of 1. And so we have x times log x squared minus 2 open bracket x log x minus the integral of 1. And so that means that the integral of 1 is just x. And so we have x times log x squared minus 2 open brackets x log x minus x plus the integration constant. We can even pull the x out since x is common in the second part here. So we have x times log x squared minus 2x open bracket log x minus 1 plus the integration constant. And so our answer for the integral of the square of log x is equal to x times the square of log x minus 2x times open bracket log x minus 1 plus the integration constant. And that was the answer that was expected. So really this brings us to the end of round 2 and round 3. Next time we'll look at round 4, and then we'll go and look at the quarterfinals, semifinals, and the finals for the 2006 integration B MIT version of it.